Welcome to video number 3 on growth models. In the first couple videos we talked about formulas for explicit and equations of linear and exponential functions and how those differ. And now we're going to talk about a new type of formula. We have an explicit formula for linear equations, and now we're going to talk about what a recursive formula is. And you may be familiar with the term recurring, which is something that happens over and over and over again. That's recurring, and so that's what recursive basically comes from. It's from repeating the same thing over and over again. And you've noticed the recursive formula looks a little bit like the explicit formula. It has p sub n, that's any term in a sequence, or was equal to the previous term plus d. That's the same d that we were talking about in the explicit formulas for linear equation. It's that common difference. So we also have recursive formulas for explicit equations, or explicit functions. And recall that the b is the constant ratio. That's take any term, divide it by the term before it, and that would give you b, the ratio, the constant ratio. And that should be the same with any consecutive set of terms. So in the recursive formula, that is similar. It has any term is equal to b, that constant ratio, times the previous term. So we'll take a look at some examples for that you can see that in. And so example 1 is to find recursive formulas for linear relationships, and here it is. You take a term is equal to the previous term plus that constant difference. So let's take this sequence of values, 7, 15, 23, 31. Now we already know this is set up to be a linear relationship, but if you look, the constant difference, remember it's p sub n minus p sub n minus 1. Any term minus the term before it. So that would be 15 would be a term minus the term before it would be 7. That difference is 8. 23 minus the term before that, that's 15, so that's 23 minus 15 is 8, and you might be able to notice 31 minus 23 is 8, or you can just say, oh, that went up by 8, that goes up by 8 constantly. That's a constant difference. So here clearly you can see d is equal to 8. So the recursive formula for linear relationships is just p sub n is equal to the previous term, p sub n minus 1, plus 8. And that is all there is to that sequence. You might note that p sub 0 here this is p sub 0, typically called p sub 0. Some sequences they say this is p sub 1, so some start with a 0 and some start with a 1, but we start with 0. This would be p sub 1, p sub 2, and so on. Okay. Now let's go to example number 2. Now we're given the starting value and the recursive relationship. So now we have the recursive formula already, and they tell us where to start. It says generate the next 5 terms of the sequence. So if p sub 0 is 11, that's the first term, we're looking for 1, 2, 3, 4, 5 more terms. And this is the constant difference, right? It's the previous term plus d. d is equal to 4 here, isn't it? That means it's a positive 4, so that just goes up by 4. That add 4 to get 15, then 19, then 23, then 27, and 31. They will go up by 4. Now how would you find p sub 10, the 10th term, or the really kind of the 11th? This is p sub 0, 1, 2, 3, 4, 5. We would have to keep going up to get 6, 7, 8, 9, 10, right? So we could just keep adding 4 at a time if we wanted. 35, 39, 43, 47, and finally, 51. So we add 4. Make sure I added 4 correctly each time. So that should be 51. And so you can see that is a little bit tougher you have to keep counting one by one. How would we find, if you look down, we're going to ask the question next, how would you find p of 100 using a recursive formula? Well, doing that, if you kept this recursive formula, you just keep having to add 4, 4, 4, 4 until you got up to 100. But note that there's not that much difference between the recursive and explicit formulas. If you know D, then you've got a pretty major part of your explicit equation already. And if you know P sub 0, which is the first term in the sequence, and in this problem they told us P sub 0 was equal to 11, and we could see by the recursive formula that D was equal to 4. So D equals 4. That means, remember, the explicit formula is P sub n is equal to D times n plus P sub 0. So P sub n is equal to D, which is 4, times n, that's like x, right? Plus P sub 0, which is 11. So there's your explicit formula. And now, to find P sub 100, P sub 100, that's where n equals 100, right? That would be 4 times 100 plus 11. Well, that's 400 plus 11, or 411, using the explicit formula. So you can see explicit formulas are preferred because it's just a lot faster to get one of the larger numbered terms. If you had to go to 1,000 or something, it's really simple to just substitute 1,000 for n and then calculate it. So explicit means it's kind of out in the open. It's just an easier, more obvious expression than the recursive formula. Some things need to be described primarily by recursive formulas, so that's why we're doing that. So now we're going to the recursive formula for an exponential relation. So remember, the explicit form was P sub n equals the first P sub 0, the initial p-value, the initial output, and then b, the common ratio to the n power. Notice that in the recursive formula for exponentials, it's P sub n. Any term is equal to the common ratio b times the previous term. So remember, n minus 1 stands for the term before the n term. And so, in order to get any particular term, you have to know what b is and multiply it by its previous term. So, in other words, if you wanted to find the 44th term, you'd have to take b times the 43rd term. So, anyway, let's take a look at an example. Example 1 here. Given this sequence of values, 6, 8, 54, ... find the formula for the recursive relationship. Well, clearly, this is not linear, because 6 plus 12 would give you 18, and then 18 plus 12 would have to be 30, and that's not 30. So this doesn't have a common difference, obviously. But does it have a common ratio? Remember, b is P sub n divided by P sub n minus 1. That is, the ratio is any term divided by the term before it, and that has to be consistent. So here is, we could take P sub 1 divided by P sub 0, or P sub 2 divided by P sub 1. So 18 divided by 6 is 3, you can see that pretty obviously. Is 54, is 54 divided by 18 also equal to 3? Well, 18 times 3 is 54. So the common ratio, b, is equal to 3, the common ratio. And so the recursive formula is P sub n is equal to b, that's 3, times P sub n minus 1. And that's it. Now you might note that P sub 0 is equal to 6. In some recursive formulas, they often prefer to write the initial term, P sub 0 equals 6, so at least you have a place to start. Basically, this just tells you what the difference is between consecutive terms. So now let's look at another sequence that they're giving us the information now. Now it says, given the starting value and the recursive relationship, P sub 3 equals 486, and P sub n is equal to 1/3 P sub n minus 1. So there's this. This is not really the starting value. That would be P sub 0. We'll have to find that later. But giving this is what we'll start with. It says generate the next 4 terms of the sequence. Well, this says to find any term, the nth term, you take 1/3 times the term before it. So if 486 is in the sequence somewhere, the third term, that's P sub 3. Then P sub 4, the next term, should be 1/3 times that term before it. 1/3 times 486. So 1/3 times 486, I'll do that real quick. 1/3 times 486. 3 goes into 4 once with 1 remainder, into 18 6 times, and into 2 twice. So that's 162. That's the next term. So we need 4, right? 1, 2, 3, 4 terms. The next term in the sequence is going to be the same thing. We take and divide or multiply by 1/3. So we'll take 1/3 times 162. That's like dividing by 3. So 3 goes into 16 5 times with 1 remainder, and 3 goes into 12 4 times. And then the next term is going to be 1/3 times 54. And 3 goes into 54. We already did that 18 times. Right? And then the next term is going to be 1/3 of 18, which we all know is 6. So that's P sub 4, that's P sub 5, P sub 6, P sub 7. Now the next one asks us to find P sub 2, P sub 1, and P sub 0. So that one just takes a little bit of thinking. If you multiply by 1/3 on the way down, you're basically dividing by 3. What would you do to work backwards from P sub 2 to P sub 1 to P sub 0? That's basically what we're doing, right? We have 486 out here. Oops. 486, and we're working backwards with, this is P sub 3. So they want P sub 2, P sub 1, and P sub 0. I guess I don't really need a comma there. But, so if we're dividing by 3 to extend in this direction, we must multiply by 3 to go in this direction. So this number, P sub 2, should be 3 times 486. So 3 times 6 is 18. We'll carry the 1. 3 times 8 is 24, and 1 is 25, and you carry the 2. That's 12, and 2 is 14, so that's 1458. Right, smaller. Now we're multiplied by 3 again, going in this direction. 3 times 8 is 24. Okay, that's 1,450. All right, that's P sub 2. 24, carry the 2. That's 20, and 2 is 22, and we carry 2. 3 times 4 is 12. Oops, I did that wrong. 3 times 8 is 24. Carry the 2. 3 times 5 is 15. Plus 2 is 17. Carry the 1. 3 times 4 is 12, plus 1 is 13. Carry the 1. 3 times 1 is 3, plus 1 is 4. So that's the next number. And then 3 times 4374. Well, 3 times 4 is 12. Carry the 1, that's 21, and 1 is 22. 3 times 3 is 9. Carry the 2 makes 11. Carry the 1. 3 times 4 is 12, plus 1 is 13. So that's 13,122 would be P sub 0. Now, I would recommend you just use your calculator to do that, so you don't make a little mistake like I did right there. So you'd get 486 times 3, and then times that by 3. You can just keep hitting times 3, and then times 3. See, this is recursive. 3 times 3 times 3. We're just multiplying each one, the next number times 3, the next number times 3. So they get 13,122. So P sub 0 is equal to 13,122. That's important because in the next question they ask us to find the explicit formula. So remember, the explicit formula is of the form P sub n is equal to P sub 0 times b to the n power. And now we know P sub 0 was 13,122. Remember, b was 1/3, right? b was equal to 1/3, we calculated up here. it was given right there actually. And so we get P sub n is equal to P sub 0, 13,122, times 1/3, right, to the n power, right here, I guess. Now, in the explicit formula, I could ask you to find the 20th term. What would P sub 20 be, for example? Well, P sub 20 would be equal to 13,122 times 1/3 to the 20th power. And that's going to be a pretty small fraction, actually. That would be 13,000, well, we've got 13,122 times, now 1/3 I'll put in as 1/3 in parentheses, to the power of 20. And that is, look at 0.000, look at all those way over there. So it's to the 10 to, that's 10 to the negative 6, so that's 0.1, 2, 3, 4, 5 zeros, then a 3, 7, 6, 3, 3, and it keeps going on and on. Okay? Now, there's a chance we can make that a fraction. This calculator actually has the ability, if it works, yeah, that one, it's too, the denominator's too big, so it won't even make it a fraction. So that's kind of a, I probably wouldn't ask a question, P to the 20th term, maybe the 8th term or something would be more reasonable, which should be 2, right? If we did the 8th term, basically we can do that same, that same problem and make that an 8 instead of a 20. And that should be a 2 there. Because we got the 7th term was 6, so we should multiply by 3 again. Okay. And that just concludes the basic idea between a recursive versus explicit formulas. And we don't use recursive formulas very much for linear and exponential functions. They're just kind of, it's handy to understand the idea. But we will study logistic relationships later, and those we will use a recursive formula for, and that's going to be, you'll be working with that more in those. Stay tuned for video 4.